So what we're going to do now is to look at electromagnetic waves in matter. So that's a different section. We will keep the discussion simple and treat linear media. And what that means is that we'll be working with the D field, which you'll remember is just epsilon times the electric field. And we're working with the H field, which is just 1 over mu times B. Okay, so these are just the permittivities and permeabilities of your linear medium. Okay, in general case, these two don't have to be collinear vectors, but in linear media, this is the case. So it's a simpler discussion. So what do our Maxwell equations look like in this case? Well, very similar to what we had. We have that the divergence of D is equal to 0. We have, once again, that the divergence of B is 0, as usual. Third one, Faraday tells us that the curl of E, okay, and here, I can write it on this side, dB dt, so this is unchanged. And now the fourth one, the Ampere-Maxwell curl of H is equal to time derivative of D. Okay, so if the medium is homogeneous, by which we just mean that the permittivity and the permeability do not depend on X, well, depend on R, on position, then things simplify. You see, because we get essentially the same equations that we had in vacuum, so all these are unchanged, and there's just one little change which tells us that the constants in the Ampere-Maxwell are different. Okay, so same as vacuum case, but I've taken the permeability to be the medium's permeability, and I've taken the here epsilon to be the medium's epsilon. So that's the same thing. So we can just transport the solutions that we've just seen for vacuum for the case of matter, provided we make these substitutions here. That means in particular that the speed of propagation, so the velocity of our waves, is going to be different from the speed of light in vacuum. So this is still going to be 1 over the square root of epsilon mu, but it's going to be different now from the vacuum value. And we're going to quantify this difference by an index where this n is called the index of refraction. So refraction, and its value is just the ratios of the medium's permittivity and permeability to those of the vacuum. Okay? So in most materials, the permeability is almost unchanged, and it's just a permittivity that has a slightly different value. So it's almost equal to the relative permittivity of the material. But we'll not go into too much detail about this. So again, all the results that we had before, they're transported to here. So for the energy density, okay, we have that in this case, again, the results are the same as in vacuum, modulo the replacement of epsilon 0 for epsilon and of mu 0 for mu. So we have this. The pointing vector looks just the same. again modulo the replacement of the permeability by the medium's permeability, E cross B, like this, and the intensity I is just 1/2 epsilon V now with this original amplitude square. Okay, so the results really completely transport directly from the vacuum to the case of linear media with these very simple substitutions. Now, of course, linear media are a bit special. They're an approximation. There's no truly linear medium in nature. You would expect that if your waves are energetic enough, they might even be able to like destroy the piece of matter that you have. So if you have extremely high frequency, high energy waves coming in, you would get lots of problems. If you had extremely high intensity, you might also get some problems. So these linear medium specializations are only valid in certain subregions of the possible parameters that you have. But nonetheless, you see how easy it is to just transport the vacuum solutions to the case of linear medium here, and that's covering most of the things that you'll want to cover. Of course, the study of nonlinear media is much more interesting, but much more complicated, and that's going to be for another course, I'm afraid.